x increases, y is decreasing right there. Now, this is not something that I will refer to them as, but I have noticed that future years, they talk about them this way. They call these power functions. Right? Don't think that that's something that's going to come back here, but power functions is just another way. 3 to the x power, 4 to the x, 5 to the x, 6 to the x. Those are all called power functions. And guys, remember, this is just an excuse for us to say bad words in math class. An asymptote is a line that y approaches as x increases or decreases. We'll talk about the shape of these graphs here. Again, this is something we covered back at the very beginning of the year in August with our parent functions idea. But we'll keep going with that. All right, let's go ahead and do this. Notice one thing that you could do is, in order to figure out the shape for any single graph, we could just make a t-chart here. Maybe some of you would start out with a 1. Here's the problem. 2 raised to the x power. 2 to the first power is?
Negative 2. Oh, 2, sorry.
Positive 2. You with us, Stephen?
Yeah.
Go ahead and put that down then, please. So you know. 2 squared is 4. 2 to the third, 16, and 32 if I keep going. What's the pattern here? How do I keep going down? Multiply by 2. So if I'm going up, what would I do? Divide by 2, right? Remember we talked about this in a quick mini thing where I was standing up there at that board talking about bunk beds. Anything to the 0th power is always 1. And if I keep dividing by 2, remember it's 1/2 and 1/4. Speaking of bunk beds, remember we talked about how they're happy on the top or bottom bunk, and they just have some similarities to what it would be on the positive side. Let's go ahead and graph these and see what we come up with. Negative 2, 1/4. Negative 1, 1/2. 0, 1, 1, 2, 2, 4, 3, 8, 4, 16. It's already off the graph. Do you see how fast the graph or this function is increasing? That already by 4 it's off the graph. This right here is an exponential growth. Notice, as x is increasing, right, from left to right, as x increases, didn't y also increase? That makes sense, because as x gets bigger, didn't my answers also get bigger? The trend is that they're going the same direction. As x gets bigger, so does y. Let's take a look at this one here. Now notice, when we're looking at this, we have a number in front of, in this case, the 1/2. If you're ever stuck, go ahead and just use your calculator. Maybe this is something that you want to do right now. Get out your calculator to make sure that you can plug this in and get the correct answers. Get out your calculator. If you don't have it, yeah.
So 5 times 1/2 times x?
Not times x. The x is in the exponent, right? So we got to raise it. Do you remember how to do that with your calculator?
Yeah, so 5 times 1/2.
Well, do we do that or do we do the exponents first?
Exponents?
For your calculator, you have to do the order of operations, right? So you would do 1/2 raised to the what power?
Raised to -2.
There you go. Some calculators can do everything at once. Others, you need to put it in there step by step. The important thing, do you know how to use your calculator? Coach Votal, the girls basketball coach, and I used to take math classes together back in college, and she seems to remember, I don't remember this, that we took a class on how to use different calculators. But, that being said, if you need help with your calculator, let me know. I can show you how to use it. Keep going, students. Don't just stop at the first one. Do the next one. All of your calculators can do this. It may be something where you're just not sure how to do it. Let me know. Happy to help. Now, some of them might be fractions, right? So maybe you want to write it as a decimal. Carson, what was your comment about the numbers, the answers, though? Yeah, they're kind of getting really small, right? Interesting point. See if that works. Sydney, did that work just to keep dividing by 2? Mm-hmm. Why do you think it does work? There's something in the problem that allows that to work. It does have to do with the 1/2, right? Now, yes, before we go with that idea any further, look back at this one. Wasn't it multiplying by 2? Isn't that number that you found, that 1/2, in that same position where the times 2 is now? Right? So that's kind of how it's doing that, right? It's not a slope. It's not just adding 7 each time. It's multiplying by a common number each time. Or, Sydney, you said just dividing by 2, right? So multiplying by 0.5 or dividing by 2. Go ahead.
Is that what makes it exponential? Because it multiplies?
Mm-hmm. Yep. A linear function from Algebra 1 means it has what we call a constant difference, right? It's adding the same number each time. That's what makes it a slope or a line. It's going up 3 every time. Up 3, up 3. But this is what makes it exponential, by making it a constant ratio or using the same multiple each time. Times 2, times 2, times 2. Or, if you're going the other way, times 1/2, times 1/2, times 1/2. Okay? Yes. Great observation. Now, Carson had also said, hey, it looks like these numbers are hard to graph. That's going to go into something we're going to talk about a little bit later today with this. But just for right now, negative 1, comma 10, 0, 5, 1, comma 2.5, 2, comma 1.5, 3, comma 0.625, 4, comma name, yeah. Students, now that we have both of these, see how, and it may be at different spots, but see how they level off, both of them? That is your asymptote. Notice right here, as x increases, so does y. This time, y decreases. Y is decreasing, right? As we move from left to right, see how the numbers are going this way for the x's? They're getting bigger that way, but this way they're getting bigger this way. They're going in opposite ways. This line right here is what we call our asymptote, where it levels off. It won't always be right here, but for this case, at least while we're exploring it, it is going to be at y equals 0. So let's explore some features. The asymptote here is always at y equals 0 for this particular one. Right here, my asymptote, y equals 0. Other things that it's asking for, a domain. Let's look at the graph for both of them. Do the graphs go to the left forever? This one clearly does, right? What about this one right here? Does this one go to the left? Yeah, not very fast, but it does go to the left forever, right? Negative infinity. Is the graph continuous? What I mean by that is, does it have any jumps or breaks? I start on the left. As I go to the right, does it jump or have any break? No, it doesn't. Scarlett, does it ever stop moving to the right?
No.
It doesn't. So negative to positive infinity here. That will be the domain every single time. Next up is the range. The range, does it go down forever? Mitchell, you're right. It levels off, right? It's always going to level off at whatever the asymptote is. In this case, 0, right? So the range is always going to be whatever number is in the asymptote, comma, infinity. So in this case, it'll be 0 infinity. Not every time, though. The range looks like it, again, levels out at the asymptote and goes up forever.
So 0 infinity as well?
For this one, yep, it will be. The last thing is, what is the y-intercept? We'll talk a little bit more about this here on the next page, but even just to get the y-intercept, what number could you always plug in for x to find the y-intercept? You could always plug 0 in, right? And in fact, students, we did that for both of these problems here. when we plugged it in on the first one, we just had a 1 as an answer and a 5 on the second one, right? Didn't I just get that from the table? But those are some things that we can find based on just really the equation. Maybe you want to make a graph, that's fine. I'm not going to grade like exact, did you put the point in the exact spot? But it will make a difference for you to be as accurate as possible. Alright, let's use these, and I know we do have to flip the page. Maybe you want to just kind of use the graph on yours while I flip the page on mine. So you could use this here. But what we want to do is we want to talk about, and I guess one more thing on the front, that this right here, as x increases and y increases, this is called the growth function, right? Exponential growth, where the second one was a decay. What we want to do is just be able to tell whether it's a growth or a decay just by looking at it here. Any guesses on, I know it's a 50-50. Would this be a growth, Caleb, or a decay?
It's a decay.
How do you know? You're right, by the way.
Because it's, well, first of all, it's a decimal. So,
Okay.
and if it's less than 1, it'll always be.
I like that second part that you said, because if I say a decimal 1.5, that's not less than 1, right?
Yeah.
So if the number in front of the exponent is between 0 and 1, that means it is a decay. So, Caleb, you're right. Maren, can you pick another one that would also be a decay? Second, third, fourth, or fifth? Looks like 0.75 is definitely between 0 and 1, right? If the number in front of the exponent is greater than 1, that's a growth. The 1 is, think about it as 100%.
I understand that. I understand the decimal rate. I think logically.
This right here means 200%, right? Definitely bigger than 1. Right?
So you're just picking up the number in the parentheses.
The number before the exponent. Now let's think about this here. If I go back to the first page to kind of prove that what you said is not always true, see on the first one there is no parentheses, but is it still the number in front of the exponent?
Yeah, so it's just the number directly
In front, right? You guys, you know those forms, right? Y equals mx plus b, right? All of those standard equations that you might use for this. This right here is typically what we see as the standard exponential equation. The number in the B position is always what I'm looking at. Any guess to what the number in the A position shows me? Not quite the asymptote.
The y-intercept?
Let's check that out. In order to find a y-intercept, don't we just plug 0 in for x?
Yep.
Let's do that on number 1. 12 times 0.95 raised to the 0th power. I get 12. Let's do it on the second one. 0.25 times 2 raised to the 0th power, 0.25. It looks like that is true. So every time that I see an A value, the y-intercept is always at 0, comma, A. We'll get to that last column here in a second, but I want to flip back to the first page, Allie, and I want to verify that that's still true. Here's what I mean. Look at the first page. We'll go back there here in a second. What number is between the equal sign and the 2 right here? An understood 1, right? Careful. People get really feisty with that word imaginary now, don't they?
Yeah.
Isn't that my y-intercept at positive 1, 0, comma 1? What number's between the base, the decay number, 1/2, and the equal sign here? Does that match up with what my y-intercept is here? It does, right? So that's the same thing that's happening. Keep that in mind here when we are going through that. Let's look at the story problem here. Scarlett, what do you think? Growth or decay?
Growth.
You got it. Hopefully that when you're putting money into an account, it is growing, right? Cole, what's my y-intercept? What's my beginning number, my starting number? It has to be 1,000, right? That's the beginning amount that you're putting, in this case, into a bank account. Students, these are all about parent functions right here. Okay? Notice if I were to look at these two, KJ, I've highlighted the yellow and now the orange. What is the difference between those? What's the only difference that I see?
3.
There's a times 3, right? That 3 really is just a stretch of 3. So, remember, if I'm looking at this, it's y equals a times b raised to the x minus h plus k. This is really right here the stretch or the compression. This is the horizontal shift. What did we say? Was it opposite on the inside or same on the inside? So it's always the opposite of what number that we see there, right? And last but death not least, this is my vertical shift. It's the same, but it is also where we get the asymptote from. Look at the beginning page. Wasn't it really a +0 at the end of both of those equations? Wasn't there not a number added at the beginning of both of them here? That's why the asymptote was at, in this case, the x-axis, y equals 0. Bless you. What do we think? Growth or decay? Bless you, bless you.
Growth.
How do you know? Which number are you looking at, Stephen?
1.35 is greater than 1.
There it is. Greater than 1.
Easy. Yeah.
The constant multiplier, what number is being multiplied each time? What is the stretch or compression? Right? That's that number in that position. Yes, it's just a 20. Careful here. What's the percent increase or decrease? How much is this growing by each time?
20.
Not 20.
1.35.
Not 1.35. Now think about what I'm going to say next. 1.35 or 135% is how much it is of its original value. Doesn't that mean it's just increasing by 35% each time? The percent that it's increasing each time is 35%. How much it is over 1. Starting value, the y-intercept, 0,20. Now, if some of the parent functions have always confused you about how to shift it, don't fret. Could you not just put in the numbers and use that handy-dandy calculator to figure it out? (20) times 1.35 raised to the negative second power. $10.97. 20 times 1.35 raised to the negative first power. 14.81. $20 times 1.35 raised to the 0th power. We already knew that was the case, right? Because we had already answered that question. 20 times 1.35 raised to the first power. 27. And raised to the second. 36.45. Again, students, I'm not coming after you and saying, I think your point is just a little bit off there. Can you please adjust it for full credit? What I am asking you to do is to look at the trend. Does it make sense that what I have here is a growth based on my equation and the graph? Let's take a look at example 2 on the next page. Very similar to what we're seeing. I do want to come back because there's some extra space there that I want to use in just a second. But look here. See if you can come up with these ideas. See if you can come up with these ideas on the far left of what the multiplier is, whether it's a growth or decay, whether it's a percent increase or decrease, and what that y-intercept is.
This is a big number. I don't know what it is. 90 times 3/5.
Smaller than 90.
What'd you say?
90 times 3/5 should be smaller than 90.
Look, 90 times 3/5 is 54. Well, let's down my x's.
right here, I think we can all agree on these three that I have written down, and we can agree that it's a decrease here. But students, it's decreasing by 40%, by 2/5. Isn't 3/5 2/5 below 1? Right? This idea comes back with what number is it less than 1? As I'm thinking about this now, this might make more sense after we take a look at it on Friday. The next idea. But here we go. We could plug the numbers in. It says 90 times 3/5, or just 0.6. We're going to raise it to the second power. 32.4. We're going to raise it to the negative second power. 250. And raise it to the negative first power. 150. Each time it's decreasing by 40%. At -2, it's way off the chart. Same with -1. But there's 0,90. There's 1,54. And 2,32.4. I want to flip back to the other page here just to give ourselves a little bit of extra space on the bottom to show you this last idea. Okay, we can come back to that here in just a second. If I'm trying to graph something like this, y equals 3, but it's raised to the x minus 4 power. Go ahead and take a second. Try plugging these numbers in. Now recall, if you plug those numbers in, it's 3 raised, and both numbers have to be in the exponent here. Maybe you want to subtract them first and just put a single number in.
May I use the restroom, Mr. Stan?
Go for it. Anybody noticing the issues here with these numbers? Are these numbers easy to put on a graph? Any suggestions on what to do? We could round it, sure. Now, I will say this, though, Cole, rounding it. 0.00137 is going to round pretty similar to this one right here, right? What makes it hard to graph is not that they round so closely together. What makes it hard to graph is if I was to look at a graph like this, the distinction between the two is not going to be very great, right? That's different if you're doing it on a computer or something like that. Anybody else have any other suggestions? Bigger numbers. Instead of just picking, this is kind of like what Sydney was saying, instead of just picking these 5 numbers every time, what if I picked numbers that gave me 0 as an exponent? What number would I have to put in for x to get a 0 as an exponent? So couldn't I plug a 4 in? If I do plug 4 in, Isn't that a 0 as an exponent or just a 1? Damien, what is another number I could plug in to get a 1 as an exponent? 5. If I continue that pattern, wouldn't it look something like this right here? The y-intercept would be 0.0123. Not well. But if we're just looking at the trend, then we could say, oh, here's how I could graph these numbers right here by plugging those in, right? Because here it is. This really means to move it right 4. Didn't this point, its original was 0. Its original was -1, -2, 1, and 2. See, this point just got moved right 4, but it has the same y value for it right there. That's all about the shifts for that. So instead of just picking the same numbers every time, think a little bit critically about it. Does it make sense for me to pick -2 through 2? Or should I kind of adjust my numbers to get numbers that are easier to graph? The last thing I want to do is kind of piggybacking on top of that is adjusting and looking at some of the transformations. Every single time the transformation, the parent function, comes from that number that's directly in front of the exponent. Y equals 3 raised to the x on the second one. What direction do I move 4 on the first one? Is that right 4? Up 4? Down 4? Left 4? It's opposite of the inside, right? So it moves it right 4. What about this 4 right here? It connects by multiplication. That's either a stretch or a compression. Stretch by 4. The 5. Dylan, which direction does it move 5? You got it. That means that my new asymptote for this specific problem would be y equals 5, and my range is 5, infinity. Notice we're still using parentheses because it never gets to 5 because of that asymptote. Parent function right here, y equals 5 raised to the x. Mitchell, how does that 1/4 affect it? Gets a little compression, just a smash of Roonies here. Y equals 3 raised to the x. Marin, what direction does it move 5? Not right 5.
Down.
Opposite of the inside, right? Moves left, right? Anytime the number has always been plus when it's connected to the x, it's always moved the opposite direction. Both semester 1, semester 2. Allie, what do you think? What about 2? What direction? Down 2. Again, that means that my asymptote is y equals -2 because it's down 2, and that the range is at -2 comma, infinity. Parent function y equals 2x.
Stretched by -3.
Samantha, what does that negative sign do? Over what? The y-axis or the x-axis? Reflects over the x-axis. Maya, last one here. Just a 3. What does the 3 do? Yep, a little stretch action. Stretchy stretch. Now, you might see, students, on today's Math Excel, some graphs on there. More than likely, they're multiple choice. That's very nice for you, right? But I hear this comment a lot. Oh, I just didn't actually have a lot of work to write down because it was just multiple choice. You could write the t-charts down, right? If you're trying to figure out what the graph is, you could write the t-chart down. That could be your work that you show. Let's take a look at inverse problems here. By that I mean taking a look at what to do to find the inverse function. Because it's 60% of its original value.
I'm mostly writing
decreasing by 40%.
Well, I only write maybe in
Let's say that if I have, they get an X number, $100, right? And I'm going to lose 40%
I write cursive better than my brother's sister.
every week. Yeah. Would that be 60% of its original value?
She's 14, but she'll be 15 on Friday.
Does that make sense?
She is in Riverside Junior High as an 8th grader.
So we take into factor everything regarding the one.
Because 1 is really 100%, right? That's kind of the distinguishing factor if it gets smaller or bigger. Maddie, I never asked. Did you find
She
your
starts
AirPods?
this August.
Did you find your AirPods?
No! My birthday's coming up. I'm still gonna make you pay.
When's your birthday? Happy very early birthday.
Happy birthday that you get to pay for your own AirPods.
Yeah.
Sure. Happy 2-day early birthday to my sister.
Yeah. They are.
I don't know. They said they know the building.
I thought you said that like when you had to find my thing.
But like, I literally checked everywhere, so there's no way that they
Yeah,
can
go for it.
You would understand that your brain is
All right, students, just going back through and reviewing. Take a look at this here. Let's start with number 2. First step is to do what with X and Y? Switch them, right? Switch X and Y, and then what do? Solve for Y, right? See what I did there?
Yes. I saw you. But that's okay. No big deal.
Let's do it. X equals negative 2y minus 6 all over 3. Switch and solve, right? What do I do first? Do I move the negative 2 over? Do I add 6 or do I move the 3 over? Right? Remember the idea is if I plugged a number in, what would be the last thing I'd have to do? Divide by 3. So that's the first thing that I do. 3x equals negative 2y minus 6. Add 6 or divide by 2?
Add 6?
Add 6, right? The subtracting of 6 will be the last thing I would do of the 2. That means it's the first thing I have to do when I solve it. followed by just dividing it by -2. If it's asking for it, because it says f of x, we could just put f inverse of x right there instead of y. Now we clearly know that those two are functions. Let's try number 1. Go ahead and do that first step. Just switch x and y.
Only I see our m's.
Or y and n, right? Really, x and y. A lot of -2's here, students. Which -2 do I move to the other side first? The one closest to the 3, JJ, or the one that's in the close to the equal sign here? Well, that looks like that's going to be multiplied, right? So I want to move this one over first because that's the last thing I would do with order of operations. Now I can divide by that -2. What is it, Sam? How do I get rid of the exponent of a 3? Not divide. Yes. You take the cube root of it. Nice. So we can take the cube root of y to the 3rd. We got to do it on both sides. So notice cube root of x plus 2 over -2. And that right there is our inverse. Try one more. Try it on your own. Take a look at number 4. Let's see what you got. Try number 4. Switch and solve. Switch and solve. Number 4.
I haven't gotten it.
How was it going to happen? Negative 8. Wait, that's multiplied or raised to yeah, it's interesting. The key raised to right. So after you
Oh, so is this? Wait,
Yeah.
would the reciprocal make it even?
They get
No, you said
It's negative 8. Oh, I'm sorry. Negative 8/3, but then positive.
No. Reciprocal just changes the top and bottom. It doesn't change that sign at the front. Because think about this. If you made it positive, wouldn't that keep it negative on the other side? Because it would be a negative times a positive, which would stay negative. Here's the first step, students.
I like black rifle.
X minus 5 and then
No.
to the side of the, to the right side of
It's
the
one
You need to move the 5 first.
How do you get it for bellows? This is the one right here.
X minus 5 equals negative 8/3 y. How do I move that 8/3 over? Excuse me, negative 8/3. Divide by,
or multiplied by negative 3.
I could multiply by negative 3. I could do it step by step. Or I could just take it, because here's Cole, here's what you're saying. Multiply by negative 3, right? And then what would you do with the 8? You'd have to divide it by 8, right? Because it's on top. Isn't that the reciprocal right there? So I'm just doing it one or at the same time, where you're doing it one at a time, which is not wrong. Negative 3/8 times x minus 5 equals y, right there. G inverse of x. Number 5. It says find the inverse of each function, then graph the function and its inverse. It doesn't matter which order we do this in. Students, how would I graph this equation here? Anybody up for making a T-chart? You could graph anything that way. Anybody up for using y equals mx plus b? If you use y equals mx plus b, the y-intercept 4, boop, up 1 and right 1. Both in my handy dandy
Calculators.
straight edge. I messed that one up, Steven. This right here, this is my original. And what I might ask you to do on the learning check is, because you probably won't have two colors, which is fine, graph one of them as a solid curve, in this case line, and the other one as a dashed curve. What's one of the points that's on this graph right here?
0, 4.
Right there, 0, 4. So wouldn't the point 4, 0 have to be on my other graph, my other line? The point 1, 5. So wouldn't that be 5, 1? Negative 1, 3. So 3, negative 1 there. I'm going to use it as a dashed line right here. This is my inverse. That is my inverse line. Now, it is asking us still to write the equation. Couple ways I could do that. I could look at this line and say, oh yeah, G inverse of n looks like it has a slope of up 1 over 1, but the y-intercept is at -4. Another way of doing that is, couldn't I just switch x and y and solve for y? Couldn't I just solve it there?
Is that a 12 or that's an M? Sorry.
See how they reflect right over that same weird fold that we did before? Break. Number 6. Graph this one. It looks like, again, you could make a t-chart. It would be really hard for me to plug number like a 1 in for x just because of the fraction. I might want to put numbers that are multiples of 5 in, like -10. -5, 0, 5, 10. I could go down 9 and then right 5, or up 9 and left 5, using that slope right there. Again, this is going to be my solid one. This is my original right here. Zero, -5. So -5, 0. -5, comma 4. So 4, comma -5. And again, I'm going to use a dashed line right here. To show that this is my inverse. We could switch it and solve it, right? To find the equation if that's what it asks for. So please keep that in mind when you're taking a look at some of these basic ideas. Finding inverses and then actually going from there.